Hello everyone, I'm Vikram Madduri here. Welcome to Softech. And in this session, we are going to discuss the chapter 2, part 2 of the machine learning density estimation. So we are going to start off with where we have stopped in the previous session, where we're discussing about the central limit theorem. So in the central limit theorem, we have denoted by xi is independent random variable with means mu I and standard deviation sigma I. Then Zm is equal to, by definition it's equal to sigma I is equals to 1 to m, and then we have this sigma I to 2 to the power of minus 1 by 2 into sigma I is equals to 1 to m xi minus mu I. So that converges to a normal distribution with zero mean and unit variance. So note that just like the law of large numbers, the central limit theorem CLT is an asymptomatic result. This is only in the limit of an infinite number of observations will it become exact. That said, it often provides an excellent approximation even for a finite number of observations, as illustrated in the figure 2.4. So in fact, the central limit theorem and related limit theorems build the foundation of what is known as asymptomatic statistics. So if we take the example of the dice again, the dice which we were using in the poker. So if we are interested in computing the mean of the values returned by a dice, we may apply the CLT, the central limit theorem, to the sum over m variables, which have all mean mu is equals to 3.5 and variance, where x of x is equals to ex of x square minus ex of x to the power of 2 is equals to 1 plus 4 plus 9 plus 16 plus 25 plus 36. These are the squares of the values that we have in the dice. So dice normally has from 1 to 6. So the 1 to 6, whatever we have the possibilities in the dice, we are squaring it and we are adding up here. By 6 minus 3.5 square is approximately equal to 2.92. So when we apply the same rule here, the same formula here, it would come up to 2.92. We now study the random variable Wm, which by definition is equal to m to the power of minus 1 sigma I is equals to 1 to m of xi is minus 3.5. So since each of the terms in the sum has 0 means, also Wm's mean vanishes. Moreover, Wm is a multiple of Zm of 2.4. Hence we have that Wm converges to a normal distribution with zero mean and standard deviation 2.92 m to the power minus 1 by 2. Consequently, the average of m tosses to the dice yields a random variable with mean 3.5, and it will approach a normal distribution with variance m to the power of minus 1 by 2, 2.92. In other words, the empirical mean converges to its average at a rate of O into m to the power of minus 1 by 2. So we'll look at the figure 2.3 gives an illustration of the quality of bounds implied by the CLT. So one remarkable property of functions of random variables is that in many conditions, convergence properties of the random variables are bestowed upon the functions too. So this is a manifest in the following two results, a variant of Cesky's theorem and the so-called delta method. The former deals with the limit behavior, whereas the later deals with the extension of the central limit theorem. Now, coming up with the Cesky's theorem, so we denote by xi and yi sequences of random variables with xi limiting to x and yi leading to c for C belongs to R in probability. Moreover, denoted by g of xy, a function which is continuous for all xc. In this case, the random variable g of xi yi converges in the probability of g of xc. So for a proof, for the theorem of 2.4 is often referred to as the continuous mapping theorem. The Cesky only proved the result of affine functions. It means that for functions of random variables, it is possible to pull the limiting procedure into the function. Such a device is useful when trying to prove asymptotic normality and in order to obtain characterization of the limiting distribution. So the theorem 2.5 delta method, we assume that xn it belongs to r to the power d is asymptotically normal with a n2 minus 2 of xn minus b leading to n of 0 sigma for a to the power a to a n to 2 leading towards 0. Moreover, assume that g is from r to the power d leading to r to the power l is a mapping which is continuously differentiable at b. So in this case, the random variable g of xn converges. So a n to the power minus 2 of g of xn minus g of b leading to n of 0 delta x gb into sigma of delta x gb to the power t. So that's the delta method that we came across. So we have the theorem 2.4, the Cesky theorem, and we have the delta method. This is a proof via a Taylor expansion. We see that a n to the power minus 2 of g of xn minus g of b is equals to delta x g of sigma n to the power t a n to the power minus 2 into xn minus b. Here, sigma n lies on the line segment b or b comma xn. Since xn mapping towards b, we have that sigma n mapping to b 2. Since g is continuously differentiable at b, we may apply the Cesky theorem to see that a n to the power minus 2 into g of xn minus g of b is pointing towards delta x g of b to the power t a n to the power minus 2 into xn minus b. So as a consequence, the transformed random variable is asymptotically normal with convariance delta x into g of b into sigma of delta x g of b to the power t. So we will use the delta method when it comes to investigating properties of maximum likelihood estimators in exponential families. There G will be the role of a mapping between expectations and the natural parameterization of a distribution. So here we have the characteristic functions. The Fourier transform plays a crucial role in many areas of mathematical analysis and engineering. The Fourier transform is equally true in statistics. For historical reasons, its application to distribution is called the characteristic function, which we will discuss in this section. So at its functions lie standard rules from functional analysis and signal processing. So we begin by recalling the basic properties. So the basic properties of the Fourier transform denoted by f r to the power n mapping to c, a function defined on a d-dimensional Euclidean space. However, let x w belong to r to the power n, then the Fourier transform f and its inverse f to the power minus 1 are given as f of f into w by definition is equal to 2 pi to the power minus d by 2 factorial f of exp to the power of exponential of minus I w of x dx. So the inverse of it would be f to the power minus 1 g of x by definition is equal to 2 pi to the power minus d by 2 probability of Rn g of w x exponential of I into w x dw. This is a theorem we have it on based on the Fourier transform. The key insight is that f to the power of minus 1, that's the inverse into f is equals to f into inverse is equals to id. So in other words, f and f inverse are inverses to each other for all functions which are L2 integratable on Rd r to the power d, which includes probability distribution. One of the key advantages of Fourier transforms is that derivatives and convolutions on f translate into multiplications. That is, f of f o g is equals to 2 pi to the power d by 2 f of f into f of g. The same rule applies to the inverse transform, that is f to the power minus 1 into f of g is equals to 2 pi into d by 2 f to the power minus 1 into f to the power of minus 1 into g. The benefit for statistical analysis is that often problems are more easily expressed in the Fourier domain, and it is easier to prove convergence results there. So these results then carry over the original domain. We will be exploiting this fact in the proof of the law of large numbers and the central limit theorem. Note that the definition of Fourier transforms can be extended to more general domains such as the groups, and we'll discuss that in further details. So we next introduce the notion of characteristic function of a distribution. This is the definition 2.7. We have characteristic function denoted by p of x, a distribution of a random variable x belongs to R to the power d. Then characteristic functions phi x of w with w belongs to R to the power d is given by phi x into w is by definition equal to 2 pi to the power d by 2 f to the power minus 1 into p of x is equal to the factor the probability of exponential of I into w of x into dp of x. So in other words, phi x of w is the inverse Fourier transform applied to the probability measure p of x. Consequently, phi of x into w uniquely characterizes p of x, and moreover p of x can be recovered from phi of x into w via the forward Fourier transform. One of the key utilities of characteristic functions is that they allow us to deal in easy ways with sums of random variables. So in theorem 2.8 we have sums of random variables and convolutions. We denote by x, y belongs to R. Two independent random variables, moreover denote by z by definition is equal to x plus y, the sum of both random variables. Then the distribution over z satisfies p of z is equals to p of x into p of y. So moreover the characteristic functions yields to phi z of w is equal to phi x of w into phi y into w. From here on we continue in the coming uh, session. So here I've discussed more about the proof of the theorem that we have discussed just now. So Okay, thanks for watching this video. Have a great day. And if you're looking out for any trainings, you can contact us info@softech.com.